100C, 120C, 150C, 160C. We'll see. Hi there everyone. I'm super excited to share with you the first batch of my 5-inch 6S battery testing results. In this video, we're going to be going through the test equipment, the test methodology. I'm going to be showing you how I collected and processed all of the data. And then we're going to be looking at how this first batch of 8 different 6S 5-inch packs compare against each other. It's a lot to cover in one video, so let's not waste any more time. Let's dive right into it. Before we dive into the test equipment and methodology, I want to take you through this first batch of batteries that we're going to be looking at in this video. So we've got 4 packs from China Hobbyline. We've got their 1200 mAh Speedy Pizza Drones pack, the 1300 mAh Mini Star, and then 2 CNHL Black Editions, the 1300 and 1100 mAh. Over on this side, we have a few different manufacturers. We've got the Tattoo R-Line 1200 mAh version 5, the Dogcom MCK Signature Edition 1380 mAh, the Onbo 1400 mAh, and the FPV. Now this is an in-house brand for unmanned tech here in the UK, which is the FPV 1100 mAh 120C. Now I know that this is just the first round of battery testing and that there are loads of other batteries from other manufacturers that you guys are going to want me to test. Battery testing is going to work just like motor testing, which is that manufacturers can send me batteries and I will test them and make a review video of the batteries and publish all of the test results. And also, if you're a pilot and you want some batteries tested, you can send me the batteries. They have to be brand new and I will test them and then ship them back to you. And the test is non-destructive. So the batteries are not going to be damaged by my testing. They're just going to have a couple of charge cycles. So if you want me to test batteries for you, you can send me them. In either case, all you need to do is email me, chris@aosrc.com, and we can sort out getting the batteries tested and the videos made. All right, so this is the exciting bit. Let me talk you through the test equipment that we're going to be using to test these batteries. What you're looking at is 2 programmable loads from West Mountain Radio. Each of these loads is rated for 500 watts of continuous discharge and a maximum peak current of 160 amps. So this system is a 1 kilowatt system with a maximum peak discharge current of 320 amps. These 2 programmable loads are connected to this USB data logger, which controls the loads and logs all the data to the PC software, which we'll look at in a second. You can see that we have these massive welding cables connected to the terminals, and then we're running a length of just normal 12 gauge wire that's the sort of a similar length to what you'd have on a quad to a standard XT60 connector. And then I also have this little USB desk fan, and I use that to blow air on the connector all of the time while the test is running to stop this connector overheating and melting, because this is actually the weak link in this whole system. When you're drawing really, really large amounts of current, this connector can get really hot, and just blowing air over it like this really helps keep it cool. One of the unique modifications I had made to this test setup is I had the power limits removed. So normally the system is limited thermally to about a kilowatt of continuous dissipation before it overheats. But you can test at much higher power levels than that, as long as you only test for a short period of time, because the system takes time to heat up. So I can test with this system at 2, 3, 4, 5 kilowatts for just a few seconds, and that's really useful for the burst testing that you're going to see later on. Before we carry on, a few thank yous. Firstly, to Joshua Bardwell, who helped support me with a lot of this battery test equipment. Secondly, to yourfpv.co.uk, who sponsored some of the batteries for this testing. There's a link to their webshop down in the video description if you're in the UK. And finally, to all of my patrons, without which none of this would be possible. If you'd like to support more independent scientific test work like this, and also get early access to my Discord server, access to all of the raw data from this testing and all of my previous testing, as well as early access to some new frames that I'm launching very, very soon, then you can join from just a few dollars a month, and there's links down in the video description. I'd really appreciate any support that you can give. I won't make you sit through the actual battery testing because basically the rig just sits there with its fans running until the test is finished. But what I am going to show you is the raw data from the two types of tests that I did. All right, so let's start by looking at the constant power discharge test. So here the battery is taken off the charger at 25.2 volts and then discharged at constant power all the way down to 3.1 volts per cell, which is 18.6 volts for a 6S pack. Now the reason that we discharge at constant power is because it's normal that as the battery voltage falls during a flight, you'll compensate by adding a little more throttle to keep the quad flying at a good altitude. So a constant power discharge is more representative. And the power that we select for this test is it's a 15C discharge. So we're taking the capacity of the pack, so 1.3 amp hours in this case, multiplying that by 15C, and then multiplying that current by the nominal voltage of the battery, which is 22.2 volts in this case, to give a power level. And that's the power that should fully discharge the pack in about 4 minutes. So that's representative of a typical length of a flight for a freestyle quad. And we can see that we get a nice smooth discharge curve. We get a little hump here around 5 watt hours, which is pretty typical for most packs. And then the battery discharges down smoothly to about 21 volts or 3.5 volts per cell. And after that, the thing just falls off a cliff and the voltage drops down very, very quickly until the test finishes. And from this test, we can get a measure of the capacity of the pack and also the amount of energy that it stores and its energy density. The next test we're going to look at is a burst test. So same as before, the battery is charged up on the charger, then it's taken off the charger and left for an hour or two to cool down to room temperature, making sure that all the batteries are at the same temperature for the start of this test. And that's because the burst performance of a battery really depends on its temperature. Once we've waited for those batteries to cool down, we can start the test. And you can see that the voltage of the pack has relaxed a little bit from 25.2 volts to about 24.8 volts. That's normal when you take a battery off a charger and leave it for a while. Then we discharge the battery at 15C for 48 seconds. Now 48 seconds at 15C is nominally 20% of the battery capacity. So we're taking 20% of the battery capacity. And so we're going to start the burst test when the battery is 80% full. And then we just step up the current. Every second we go up by 2C. So 2C per second, and we keep stepping up and up. So after 10 seconds, we'll be at 20C, and after 50 seconds, we'd be at 100C. So we keep stepping up the discharge current until the battery hits 3.3 volts per cell, and then we stop the test. And this avoids an issue that I had when discharging to lower voltages than that the battery actually starts heating up a lot, and you can then get into this kind of thermal runaway situation that I wanted to avoid. So we go down to 3.3 volts per cell, and that's a safe level to discharge down to. And we see how much current the battery can supply when it's at 3.3 volts per cell from 80% full. And that gives us our maximum power, our comparable C rating, and things like this. Once we've completed those two tests on all of the batteries, we can export all the results to CSV files, and then it's really easy to automatically process all of the data in Python to extract all of the key performance parameters that we care about for all of the batteries. So now that that's done, let's take a look at the results from this testing. All right, it's time to look at some test data now, starting with battery capacity. And this is measured during my 15C discharge test. We're measuring the capacity in amp hours, and we shouldn't expect this to precisely correspond to the manufacturer's stated capacity, because that will have been measured at 1C and I'm measuring at 15C because that's a more typical rate of discharge for FPV. What we do see though is that there's pretty good correspondence between the stated capacity and the capacity that I get during the test, which is good. Although that said, the larger packs, the 1380 and the 1400 milliamp hour packs, delivered a little bit less than their stated capacity, and actually were pretty similar to the 1300 milliamp hour packs that I tested. Overall, this doesn't matter too much. We're going to be looking at the energy and the energy density of the battery, which is a better comparison for performance. That brings us to the next chart, which is energy storage. Now this takes into account not just the current times the time, the amp hours that the battery can deliver, but also the voltage that it delivers. So a battery that delivers the same amp hours at a higher voltage delivers more energy, and so that's going to give you a longer flight time. What we can see is that Again, the energy storage corresponds pretty well to the stated capacity, with the larger capacity batteries delivering more stored energy. Again, these larger packs, the 1380 and the 1400, are delivering a little bit less energy on test than what they're rated to. So again, not much more than the 1300 milliamp hours, but overall this is pretty good, and none of the batteries are wildly different from their rating. It's not just energy storage that we care about though, it's also energy density. It's easy to make a battery that stores a lot of energy if it's very big and very heavy. But if you can make a small lightweight battery that stores a lot of energy, that's really good for flight performance and flight time. Here we see more variation between the packs, with the CNHL Black 1100 milliamp hour having the lowest energy density, so it's storing the least energy per gram of weight, and the Onbo 1400 milliamp hour having by far the best energy density, nearly 0.135 watt hours per gram. So if you're looking for a battery that is providing a lot of energy in a very lightweight package, the Onbo 1400 is definitely going to be the one you want to look at. But the Tattu R-Line version 5 also does really well. Overall, this is going to be more useful for people who are thinking about flying for a long time than necessarily people who are looking for maximum performance. For those of us more focused on performance rather than flight time, we're going to be more interested in the results of the burst testing. And here we're looking at the maximum power that the battery can deliver at 3.3 volts per cell when it's 80% full. So the more power that the battery can deliver under these conditions, the more dynamic and powerful it's going to be when you punch out. What we can see is that the larger batteries with the higher C ratings do tend to perform better in this test, with the Dogcom MCK 160C pack delivering the most power, more than 1600 watts, and the CNHL Black 1100 milliamp hour 100C rating delivering less, about 1050 watts or so. So you can see there's quite a big difference in the performance between these packs. We've got about 50% more power with the Dogcom MCK compared to the CNHL Black, and the Tattu R-Line also does really well in this test, delivering a little bit less than the Dogcom, but it's really getting up there. Similar to energy and energy density, we also care about the power density of the battery. So this is taking into account the weight of the pack. It's no good having a battery that's really, really powerful if it's really big and heavy. So we're looking at the power density of the battery in watts per gram to see just how good the performance of the pack is. And what's really interesting here is that the order of the batteries changes quite a bit when we're looking at the power density. We can see that the best performer is now the Tattu R-Line version 5 because it's very nearly as good as the Dogcom MCK, but it's significantly lighter. And then we have the FPV 1100 milliamp hour pack, which, although it wasn't the most powerful, it's very lightweight. So when we're looking at power density, it's performing really well. So if you're looking to build a lightweight quad that has lots of power, the Tattu R-Line and the FPV 1100 milliamp hour are both really, really good choices. Moving further down, we have the Dogcom MCK next. So the power density is not quite as good as the Tattu or the FPV, but it's still above 7 watts per gram, so it's doing pretty well. And then we got down to something like the CNHL Black, only delivering about 5 watts per gram. So you can see that the difference between the worst and the best batteries in terms of power density is more than 50% difference. So about 5 watts per gram for the least power dense, and over 8 watts per gram for the most power dense. So depending on your choice of battery, you really can get quite a big difference in terms of that burst performance. We can also use this burst test to produce a comparable C rating between batteries. Now this is not going to be the same as the manufacturer's C rating because they will typically start with the battery fully charged and then discharge it immediately down to, maybe 3 volts per cell and see how much current it can deliver. My test is less aggressive than that, so I get a lower number, but this test is comparable across all the packs. And what we can see is that the Tattu R-Line and the FPV deliver the highest C ratings. They are above 60C, above 65C in fact. The CNHL packs come out a bit lower, they're 50C or a bit below. Overall, I don't think C rating is that useful. I think power and power density are more useful metrics because you can kind of game the C rating just by writing a different capacity on the pack. So you could write, 1,000 milliamp hours on that Tattoo R line, and then wow, suddenly your C rating is 20% more. So I don't think that's particularly useful. You can't game power and power density in the same way, because whatever number you write on the pack, it's still going to deliver the same power and it's still going to weigh the same. As well as energy and power density, we also care about voltage sag during a flight. And to show this, I produced this graph of voltage versus capacity. So capacity runs from 0 all the way up to 100% at the end of the test. And we can see what voltage the pack is able to maintain during that whole run at a 15C discharge rate. And overall, the difference between these batteries is a lot smaller than what I saw with the 1S packs that I tested. But there is still a little bit of variation with the FPV, the Tattoo R line, and the Onbo 1400 and the Dogcom packs, all being able to maintain just a little bit of a higher voltage overall compared to some of the less expensive CNHL packs. This graph can get a bit busy, so what I like to do is I like to take the voltage at 50% capacity and then show that on a bar chart. And we can see that there's not actually that much variation between all these batteries. We've only got maybe 0.2 volts between all of these different batteries, which is not very much when considering that I was seeing, as much as 0.1 or 0.2 volts on a single cell with the 1S testing. But you can still see that there is some spread in terms of performance across these different packs, with the VFPV and the Onbo packs demonstrating the least voltage sag, and the CNHL Black and Speedy Pizza cells showing the most voltage sag. And if you're really concerned about voltage sag, you want to maintain the highest possible voltage to get the most RPM at the prop throughout the flight time, then you're going to want to pick one of those packs that has a higher voltage at 50% discharge. All right, so that brings us to the end of the test data. And what I've done is I've taken the 3 key performance parameters, so energy density, power density, and voltage sag, and combined them all together to give an overall score for each battery. And we can see that overall the Tattoo R line version 5 1200 mAh comes out on top out of this first batch, with the CNHL Black 1100 mAh 100C bringing up the rear. The real standout kind of value performer in this, from my perspective, is the FPV 1100 mAh pack, which, despite costing about £10 less than the Tattoo R line, performs very nearly as well. The key here is that the cheaper batteries are going to be fine for you if you just want to kind of cruise around or you're not too worried about top-end power. Where you're going to see the benefit from the more expensive or more high performance batteries is really in those punch outs and in that kind of burst scenario where you're looking to get the maximum performance out of the battery for a short period of time. And that brings us neatly to the end of the video. I hope you enjoyed it, learning about the test equipment and methodology, as well as seeing the data from this first round of testing. And I hope that this information helps you pick the right battery for your next build. If you're a battery manufacturer or an enthusiastic pilot who wants to get some batteries tested, please reach out to me, chris@aosrc.com, and I'll help sort that testing out. And if you want to support more independent scientific test work like this, please do check out my Patreon, and there are links to that down in the video description. That's all I have for you for today, so until next time, I wish you all very, very happy flying.